final lecture in 4820. Mohav and I will both be seeking to some degree entertain you today, to give you a sense of closure, and maybe also to put your minds at ease about the one remaining thing you have to do this term regarding this class. A little 4-hour exam, nothing to be afraid of. We'll try to help with exam preparations also today, and please keep in mind, if you maybe weren't here last week, there will be one more laboratory session next week on Monday, where Elena will also be available to talk through questions from previous exams. So you should have ample opportunity to get your questions answered. And then it's a little more than a week. I think Friday next week is the actual exam, and then you're done with this class. So today, we actually want to leave at least half, maybe more, of our time for exam-related preparation. We suspect you care about that. But we want to make one relatively high-level attempt to sum up, to give you the large picture. Our attempt at identifying some of the important high-level points that we've covered in the past. What is it? 14 weeks, I think. This is the 14th lecture in this series. Once we'd introduced a programming language that was mostly new to everyone, and maybe felt somewhat weird to most of you. The first problem we point to was talking about similarity between observations and questions of grouping observations. In our case, these were words in context, but the technique, as all of the others, would be applicable to any number of abstractly similar problems. And this question of how do we represent membership of a group, a class, and how do we predict it given one observation. And from point-wise observations, that is one observation at a time, we then move to sequences. In our case, these were utterances in a natural language, strings of words of English mostly for us. And we introduced probabilities over strings, using what we call language models, n-grams, that operate right at the surface, the observable units, but taking into account the sequential nature of the observation. Then we added a first layer of abstraction, of analysis, if you will. On top of the words, in our case, we introduced notions of the lexical morphosyntactic categories, the parts of speech, noun, verb, proper noun, past tense verb, preposition, that kind of thing, and introduce these as hidden variables, things. So the first time something that we cannot directly observe, the hidden layer, and modeled that in a framework called hidden Markov models. That has that one layer of analysis, but still is by its nature sequential. It's still linear. And from there, I'll go into a little more detail about all of these in the slides to come. From there, we added hierarchical structure. That was a jump in terms of essentially stipulating an arbitrary and an unlimited number of hidden layers. You might say any level of embedding in our trees is a hidden layer of structure, and they're organized not only sequentially, they're organized in a hierarchical structure in the sense that they are dominance relations. Constituents are groups of things, and they nest they nest within each other and form a hierarchical structure. And we motivated the use of formal rules, the grammar of a language. That was the declarative perspective on these structures, and then turned to for 2 weeks, 2 lectures, to a procedural view. How can we actually compute? How can we find the valid structures given an observation, a string, and a grammar set of rules? And then relatively briefly towards the end of last week's lecture, we also again added this layer of probabilities to approximate this notion of the one structure that is the most likely one, the intended one. So that's the sort of large picture, the trajectory we took. And so this is an attempt at what may have felt like many individual dots that we just threw out. They actually form a picture. So once we connect them, and by now we hope you're in a good position to see these connections and to see the similarities, the parallels that hold across the various segments. And in all of these problems that we have addressed, we deal with data-driven learning. It's machine learning in the sense that there's some data that implicitly defines the rules or the patterns of how the data hangs together, of the hidden structure that we cannot observe for those models where actually there are hidden layers. And we seek to learn these generalizations, these rules, these patterns from the data that we can observe, and a lot of that observing is actually counting observations. But some of the variation is what assumptions we make about the underlying structure and the associated probability model, and what decisions we make about how much context to take into account. For the pointwise observations, we approach these out of context. Well, we consider them one by one. We actually learn their position against the contexts where we observe them. But then later on, we don't assume that there's any correspondence, structural correspondence holding between individual observations that we might want to classify. Thank you, Mohav. So the contexts in our pointwise modeling were bags of words. Other words that a word that we're seeking to position in this space co-occurs with. In language models, the contexts are prefixes, previous n-1 preceding words in an n-gram language model. Pretty much the same in terms of which context do we consider for the HMMs, but the language modeling part of the HMM actually applies, it holds at the hidden layer. So we consider contexts of assumed, hypothesized previous states, parts of speech. And we connect the hidden layer to the observation layer through the emission probabilities, and those are only at the current observation. And finally, in the hierarchical structures, the contexts that we consider in a context-free grammar, almost sounds contradictory, is local subtrees of depth 1. So as long as the context requires me to put an NP here, somewhere in the tree, then into that context I can put all subtrees of depth 1 that I can instantiate all rules whose left-hand side is NP. And I cannot constrain from that node further down into the tree. Let me just connect my pointer here. I feel clumsy when I can't walk around. So that's one way of connecting the dots. Another sort of cross-cutting theme was choice of data structures. we often have an abstract model, and when we implement it, we need to map that onto implementation choices, that is data structures, and these choices actually matter. We've often made you work with what a couple of years ago would have been called large-scale data sets. 1 million words is maybe no longer large scale. We're now in current research, vector space modeling will maybe be applied at billion-word corpora. Maybe even 50 billion words that we can extract from a web crawl. But certainly non-toy data sets. The Penn tree bank is still used in much active research. How to actually represent our sparse matrices or transition and emission probability matrices in the HMM and the trellis, the data structure that the Viterbi algorithm operates over. These are important choices, and we hope we've made that tangible and clear to you, and that applied to all of the problems that we considered. For implementation, we didn't give you a choice. We introduced you to Common Lisp, and from the midway feedback, some people actually seem to have enjoyed that. Some clearly didn't. And yeah, that's not surprising. It's in some respects may feel like a weird language, or the environment that we gave you, an integrated development environment using Emacs as the front end. But if you got to, so a couple of people said in the halfway evaluation, why can't we do this in Python? And part of the answer is it actually would be difficult, if not impossible, to build an HMM, even more importantly, chart parsing implementation in Python that will run at the same efficiency. Because one of the differences, so Python is a modern version of Lisp, some people might say, but it doesn't have native code compilers. It runs in bytecode, so it's a scripting language. Lisp is a language that has been stable for decades now, has very mature native code compilers. And certainly for the larger data sets and the more complex problems that we solve, that actually mattered. I actually haven't tried myself, but I would be skeptical that you can do the chart parsing in pure Python. You would look for solutions that would allow you to have more efficient variants of some of the core pieces. Call out to native C code or something like that. And more high level, we spent a little bit of time on observing that Lisp is an early representative advocate of what characterizes functional programming, even though a lot of the programming we have done was not pure functional programming. We had many side effects. I mean, the trellis is a data structure that strives on side effects. But still, functional decomposition functions as first-class objects that we use to parameterize built-in library functions, for example. We have observed and used that. We have, in parsing, for example, that's a problem that is inherently recursive. We don't know the depth of the tree. Anything that traverses trees or graphs typically lends itself very well to recursive approaches. And we have dwelled to a certain amount on how much memory does it actually take to represent a pair of things. And what are the differences when I pass around a large object as I do in Lisp, essentially by sharing a pointer when I have an array and call a function and give that array as a parameter. The array, the object, is not copied. What the function receives is internally a pointer. It retrieves access to that object. And we have noted, you have noted at times that these choices actually make tremendous differences. And some sort of throughout the lecture today we'll comment on the exam. How much Lisp do you need to know for the exam? The high level properties, some of these choices we've made? Yes. Some of the considerations that we discuss in comments on our model solutions, choices of data structures often. Yes. The fine points of Lisp syntax? No. We won't ask you about what won't we ask you about? Well, I don't want to make that kind of promise. But I was going to say we won't ask you about the difference of ampersand key versus ampersand optional versus ampersand rest parameters. But then I wasn't sure I wanted to promise that much. That's not syntax. That's a high level named parameters, order coded parameters, optional parameters, somewhere in a gray area. But since we've now discussed it, I guess you can assume it's not going to be part of the exam. But specific questions of syntax and individual function names, no, you don't need to know that for the exam. You need to know that when you program, which we hope some of you might continue doing in Lisp even. If nothing else, Lisp has helped level the playing field. You all started roughly in the same place. And if nothing else, this experience has also given you the experience of learning a new programming environment, which when you go and job interview, the company where you interview, they might not appreciate that you have learned Lisp. There are a handful of companies that still appreciate that. Computas is one of them. There's still companies who recruit, who sort of approach us and ask, anyone you could recommend from this class? But that's a small number of companies. But they will appreciate that you have learned a new language kind of on the fly. This is not a Lisp course, but we've made you program and learn to program efficiently in a language that you didn't know before. And that's a useful experience, I believe. That's part of our motivation still in forcing this ancient language on you. Okay, now one slide each on the specific problems. So the first application of machine learning to natural language understanding, natural language processing were vector space models, spatial metaphor. These are not probabilistic. It's machine learning, but there are no probabilities yet. It's this putting things into this highly multidimensional vector space. And that's a multidimensional coordinate system, and the feature vector essentially denotes a point in that vector space. And we applied that metaphor to what is often called distributional lexical semantics. Lexical semantics because we equate usage with meaning. It's the distributional hypothesis. So meaning of words, that is what lexical semantics means. Distributional because we assume that the company in which a word is most frequently observed tells us something about its meaning. And how do we define company? That's again this question of what are the contexts that we consider indicative, that we that our machine learning algorithm or machine learning is sensitive to. And for our vector space models, we kept it sweet and simple, bags of words. That is some window around a target word. Counts of other words observed in that window. And we briefly talked about the relevance, the importance of normalization, reducing different forms of the same word. To dance, dances, danced, dancing are all forms of the verb dance. And lemmatization or stemming help to normalize uninteresting variation in the training data. We assume that the meaning, the lexical semantics of all forms of the verb dance is shared. And so it makes sense to define our target words and our context features in terms of lemmatas or stems, the base forms. We talked about two different notions of measuring similarity between these feature vectors in the space. Observed that frequency differences can actually be important in computing normalization, in computing or in deciding on degrees of similarity, and observed that length normalization of our vectors takes out these frequency effects. And on the implementation side, observed that these are very high-dimensional vectors, essentially the vocabulary of in our bags of the union of words in these bags of words. Each word is one dimension, so we end up with very high-dimensional vectors, but they're very sparse. They'll contain a small number of non-zero counts, and conceptually all of the other dimensions have zero counts, and so that is an important property to consider in choosing a data structure. Sparse vectors, sparse matrices, important choice in much scientific computing. Then with this distributional take on lexical meaning, we looked at two possible computations, two tasks that both relate to group formation. One where we assume that there is a predefined inventory of groups, classes, and given an observation and the ground truth, the gold standard of corresponding classes, we can learn to predict group membership for unseen objects, words that we have not seen in training. That's supervised learning, because the answer, the predicted answer, the classes need to be present when we train. We need labeled training data. Clustering, in many respects, is it's not the inverse. But there, the grouping emerges from observations over the data. It's not predefined. It's not something that we stipulate. It's something that we also discover, learn from the data. And in that respect, clustering is unsupervised learning from unlabeled data. So that was the one instance of unsupervised learning that we looked at. And abstractly, it forms groups of similar objects. And then the inventory of groups, in a sense, is a byproduct of that. So clustering does the grouping, and then I can observe how many groups did I end up with. And I don't have a priori meaningful labels on these groups. They are just extensionally defined as those observations that end up in that group. I need to move on a little. We introduced two vector space classifiers, still all geometric models in this spatial metaphor, Rocchio and KNN. One is based on this notion of a centroid, the representative of a group of observations. The other is K nearest neighbor, that actually determines group boundaries based and membership based on well, a set of neighbors, of points that are in the neighborhood. And this distinction corresponds to linear versus nonlinear decision boundaries, where in a two-dimensional space I could either draw a straight line that separates the classes, or I couldn't. And differences in the assumptions we make, and also differences in the complexity in training versus complexity in prediction. And we briefly discussed all of these. And that was the first point where we needed to evaluate. We needed to ask how good is what we do, to judge quantitatively, to judge objectively the success of the machine learning that we have applied. And we introduced accuracy, which we observed is not a very good, very informative measure when there are class imbalances, when one class is a lot more frequent than another, and hence moved to these measures that we've been using throughout the rest of the course, precision recall and F-score, combining the two into one, which come from information retrieval originally. And at one point briefly applied these or generalized these to evaluation when we have more than one class, multi-class classification, where we could either average at the instance or at the class level, and that would correspond to micro versus macro averaging. Many of these points we would like you to take home, so that's why we put them on the slides here today. Then we also devoted one lecture on clustering, the unsupervised vector space learning, and had only one looked at only one algorithm, k-means, which essentially forms clusters by minimizing the distance, mutual distance. I realize I'm a little rusty on this since I haven't taught it for several years. So you correct me when I misspeak. You want to take over? You don't. But that's the Voronoi tessellation, isn't it? Yes. So where we find that partitioning of the space, the so-called Voronoi tessellation, that minimizes those distances. And we approximated that in an iterative process where one of the issues we discussed is where do we start, and that the initialization, since it's an approximative, well, by nature, there's no ground truth, an approximative algorithm. How we choose our starting point can actually influence the outcome. And there are a number of parameters. How long do we iterate? When do we stop? Which value of k do we consider? And what similarity function do we apply, since we had introduced two and there are more candidates. We didn't talk about hierarchical clustering this year. We didn't at all. No, we just skipped that. At that point, we had done some non-trivial machine learning, and vector space modeling still is a very relevant paradigm, even if it may feel simplistic in comparison to some of the things we did later on. Then we introduced probabilistic models, where probability distributions take center stage. And essentially they are distributions abstractly over different configurations, and what these configurations are depends on the model that we choose. Pure sequence of things, a string of words in a language model, sequence of things with associated hidden labels in an HMM, or context-free hierarchical structure. And these can be used for different purposes. In fact, some of them can be used for more than one purpose. And we briefly observed that language modeling we can do using n-grams, n-gram language models as we introduced them, but we can also use an HMM as a language model. We can in fact use PCFG as a language model. We could determine the probability of a string. That's the task in language modeling, as the sum of the probabilities of all parse trees for that string. Just as in the HMM we set the probability of a string, we can model as the sum of all paths of all state sequences through the HMM given that string. So we can play the same trick and use the models with more structure also for the simpler task, but not vice versa, obviously. An n-gram language model cannot tell us anything about the likely sequence of parts of speech, the hidden layer. And we can break them down into linear versus hierarchical, so sequential n-gram language models, and HMMs versus hierarchical grammars, and sort of work through this trinity of problems, which string is most likely, which tag sequence is most likely given a string, and which interpretation, which tree structure, which we use as a proxy for what does it actually mean, is most likely given a string. Sushi with tuna or sushi with chopsticks. I'm inclined to skip some of these slides, if you agree. Put them out. This is a selection of things you've seen before. This is intended as a reminder of things you know, and putting them in a large perspective. I don't think I need to go through the details here, but the goal again is to make visible the commonalities. So that's the color coding. So in all three cases, there's a central invocation of the chain rule. In the sequential models, we depend on a Markov independence assumption. All but the n-gram language model introduce a hidden layer of abstraction. I've said all of these things, I feel. They all use maximum likelihood estimation, essentially converting raw counts, raw frequencies, into relative frequencies and using those as probability estimates. And they differ in what we condition on. For example, the left-hand side of a production rule from the grammar is the conditioning context for the PCFGs, because they're plugged into a specific position in a tree where the root of the tree is defined, required to have the start symbol. So that was the formal mathematical side of things. And then we had, for each of these algorithms, in fact, we didn't really talk much about algorithms operating on language models, relatively trivial. The challenge really is that you want very large language models, and you need to effectively efficiently look up probabilities based on a context of, I think Google's currently using 9-gram language models in some of their MT systems. And you can imagine that these are huge data structures. And so they're really, all of the engineering goes into looking up a probability given a context of 8 preceding words efficiently. That's not a table that you fit, that's not a hash table that you fit into memory. For HMMs, we looked at the Viterbi and the forward algorithm, and the forward algorithm calculates the probability of a string, effectively sums, and uses an HMM like a language model. The Viterbi algorithm, often called a decoding algorithm, finds the most likely hidden state sequence given a particular observation sequence. And these were dynamic programming algorithms that take advantage of the recursive structure of and decomposition into sub-problems that frequently need to be recomputed. And it turned out that once we had put this generalized chart parsing framework into place, that the very same ideas are applicable in the hierarchical parse forest. So Viterbi decoding over the parse forest, extracting the most likely tree, we can formulate very similar to HMM decoding. Only the conditioning contexts are different and the data structures that we use to retrieve them are different. So in the last a little more than third of the class, all of the algorithms actually were dynamic programming algorithms, but we didn't dwell very much on that. We assume you recognize that property, and dynamic programming properties, I think, are there's a dedicated class for that. The common theme here is compute these types of problems that decompose recursively into repetitive or overlapping sub-problems efficiently. Right there we have that. So the color coding does it all here. And evaluation in all machine learning. If we can't say how good is it, we can't do science. We can't talk about one algorithm in comparison to another one, or even one parameter selection, 3 grams versus 4 grams, or one way of smoothing, of making the maximum likelihood estimation deal with unseen events. So there are many variables in how I actually put these to use. And a lot of sort of our actual research work is to explore experimentally that parameter space for a given specific problem, which typically means one language, one set of training data with specific assumptions about the inventory of parts of speech or the correct way of doing syntax. Find the algorithm and its parameterization that gives premium performance. And hence evaluation is really key to doing science in that space. And for the HMMs, accuracy actually worked out well. We could do precision recall there, but we don't have to because we always have the same number of so in all competing taggings for one string, there is a constant number of decisions that we're making. Hence, there's not this imbalance challenge that made us put aside accuracy as an informative measure in the classification problem. For parsing, we actually didn't talk much about coverage. And near exclusively about parseval. But of course, where a parser may actually not be able to recognize a string, it may only generate a subset of the actual language. Partial coverage, that was the case for the parsers we built, because they had no way of dealing with unknown words, can be a practical problem. So. Typically, one would hope to build parsers with perfect coverage. And then the quality of the trees that it delivers in comparison to a gold standard is the main metric that we will use in comparing two different parsers. And that's the Parseval metric. So that completes my sort of high-level attempt to cut through the semester and draw some parallels or point out some parallels. And now that was fun. All good. In thinking about the exam, here are some reminders. On the course page, we have for each week indicated sections, subsections from the various books that we have used. In addition to those, so that's the background reading. Of course, I mean, you've read that more than once, haven't you? All of you. We assume that you have the lecture notes, the slides, and in addition to that, our model solutions, and maybe most importantly, also the commenting that we do in those model solutions are something that we assume you all have internalized. The exam is a closed book exam, so no need to bring any of these materials. It's this coming Friday, I think, at 2:30. Lasts for 4 hours, even though we're encouraged to to give an exam that a very good student might also be able to complete in less than that, in 3 hours. That's very hard for us to estimate. It still happens that we underestimate how much time goes into answering one question. And then, of course, in grading, that becomes apparent, and then we actually adjust. So I hope that many of you, as what is it, 6:30 approaches, feel I'm done with this exam. That's what we're aiming for. And you can tell us afterwards whether that worked out. There are at least 2 different locations where you write your exam. So those who are fresh students from outside the University of Oslo, check in, well, everyone check in StudentWeb, but it's important that you go to the right location. We are not involved in running the exam. And you're just expected to show up with the right documentation. What is that? Your study card, I think, and the photo ID. Maybe some food for the 4 hours and a pen or 2. That's all you need. And we'll give you an exam text in English and only in English, but you're free to answer in any language that we can, in English or any form of Norwegian. I was going to say any language that we can make sense of, but that's casting it a little wide. All exams will be graded by 2 people independently. That will be Mohav and me for many of them, but we'll also need additional help. Probably Erik, but he doesn't know that yet, Erik Veldal. And then the 2 graders after the fact compare their notes and resolve where they disagree. So Norway has a fairly advanced grading culture, I think. You should be fairly sure that you get a fair assessment. And if not, there's still measures that you can explore. This is actually from last year, I now realize, because Erik and I disagreed slightly on what we would like to recommend here. What you should not attempt to do is what we often call the brain dump. So we ask about something, and you say, I'm not sure I know what that is. I'll write down something that I happen to know. No credit for that. And if you do a lot of that, it actually irritates the grader, because we need to search for the nuggets that may actually have to do with the question. Keep your answers to what we ask about. And keep them short or concise. Don't try to elaborate unnecessarily. So keep it to what is relevant is maybe the key message here. Whether less or more is more. More that is relevant is more, but less that is irrelevant is also more. So relevant really is the key message here. High recall and high precision. Everything that we expect to find should be there, and you should state it concisely and accurately, so that we can actually be sure that we understand what you're saying. Various points we've introduced terminology, and it's nice for us to see that you recognize concepts and can call them the right name. So where you feel, this is actually what we called the sparse data problem or local ambiguity, use that term. And you will be able to tell from the exam text the proportion, the relevance, how many points, what percentage of the total each question, so you can sort of work through them in any order that you find strategically helpful. The questions with the highest points first, maybe. We'll try to make the first question a warm-up question usually, so that will not be the question with the highest points. All right, so that was the sort of high-level announcements regarding the exam. Before we use the second part of today to actually answer your questions about one specific exam that we have posted, actual exam from 2014, I think. Any questions about this? The logistics and our thinking about exam strategies? No. So then one thing we didn't announce very overtly, we've been following relatively closely how well you do on our obligatory assignments, because that's very important feedback to us. Our goal is not to keep people from taking the exam. On the contrary, our goal is to enable you to take the exam. But obligatory exercises are mostly there to keep you working throughout the semester and to solidify things that we introduce abstractly and theoretically in the lecture through actual implementation. So as every year we observe how many people dropped out. This rate is actually fairly stable by now. That's, what is it, 20%? We have an almost 20% increase both here and here compared to last year, so there are more people taking this class now, but the what we call the retention rate, people who thought I might take this class and actually submitted for the first obligatory exercise but then disappeared at some point, is pretty much the same as in previous years. And this is, in our view, fairly decent. Of these, all but one qualified for the final exam. So that one, of course, that's sad. I mean, you sort of go that far and then you really very clearly, despite all the effort we put into making it possible to accumulate the required points, you're well below that threshold. And of course, there's a spread in some who just about qualified. Some obviously just put in strategically the effort they thought was required to get the missing points on 3B. And some who sort of went all the way, and at least one, maybe more in fact, who even did the optional question on our last, was there more than one? So that's actually 3. More pointed out another outstanding participant, and those we would like to honor now. So in total there were 50 points, 50 regular points, and 3 of you actually landed on 2 at 47 and 1 at 49. Of course there were bonus points, but that's very impressive, we think, and hence we find it appropriate to actually name you and see whether you're here. And then there will actually be a prize. So Ivan, Lars Christian, and August are those 3 who have 47 to 49 points. And if you're here, then some of you may know this prize. We have more sizes, so we might have to. This is a. I mean, you might wear this to the exam if we actually find one in the right size. So that's Ivan, Lars Christian, or August. Lars Christian is not here. So big round of applause. Really well done. I think you maybe want slightly bigger than that. Let's maybe take a break here. There are many more who did really very well. So the sort of top field was relatively narrow. There were 12 people or so that we sort of felt we had to grade on 3B. You haven't received your 3B feedback. So we had to strategically look at those who were just barely or very close to the passing threshold first. so that we could register that, and then to do this, those who were near the top. So there's a fairly dense top field also. At this point, let's take a break and come back 20 past, and then do the sample exam.